So in this first part, essentially what I will try to do is to give you a quick survey about the foundations of decision theory, some of its recent developments, and in terms of giving you context, I will also try to outline the relations between this research and many similar researches in other fields, as well as to mention some of the typical applications of these days. So I will start from the very beginning, but then I will get to pretty much what's been done in these days. Evidently, I'll have to skip a certain amount of minutes, even now there is plenty of time to do lots of things. So the basic problem in decision making under uncertainty, you have a decision maker that has to rank a set of actions from the best to the worst. And the uncertainty aspects is in the fact that the consequences associated with these actions are not ordinary facts. It is so because the consequence associated with an action depends also on the realizations of factors that are not under control of the decision. Think of pretty much any problem that you want to think of. Obvious examples would be issues associated with climate change, investments in assets, insurance in general, any problem of an observables would be with these features, etc. So basically, the idea is the following: an environment is specified by value certain parameters. Say, this is an example like this, when you specify the temperature, climate sensitivity, etc. Once you choose an action, if this is the specifications of these parameters, you obtain a certain consequence. If the specification, the environment is different, the same action would be associated with another consequence. So basically, this very basic observation essentially tells you that one way of modeling these actions that are available decision maker is that regarding them as mappings from a set S, which whose points would be exactly the specifications of all the factors that define an environment. So you should be thinking of a point in S as the full specification of an environment that the decision takes place, and C is a set of consequences. Okay? S is called the set of rules, C displays the set of possible consequences. I forgot to tell you that since the purpose of this part is essentially create the background for the second part, interrupt me anytime that you think that I am quick take whatever it is that you have to. Okay, so mappings, these mappings are regarded, these actions are regarded as mappings from S, set of states to set of consequences. If you assume that the decision maker has a utility on consequences, which means that it is able to rank its consequences by means of real numbers, you can consider the composition of an action with these utility functions and then essentially identify actions with real value functions. And there is a clear advantage to do that because, in this way, the set of actions via this identification clearly takes a lot more structure. Okay, so aside from this, there is an intuition that you can use. In fact, we will be using it momentarily. Via this identification of actions, real value functions, you can think of an action alternative as an asset that pays contingent on the realization of a state. Okay, you will see why I bring this up. This one, you will see it in the next slide, in 2 slides. Before we do that, there is a point that I would like to underscore. It's not going to be important in this first part, but it's going to be important in the second part. So as you will see, we will be giving the set of states the structure of the measurable space. And we will do so evidently by defining a sigma algebra on it. Now, what is this sigma algebra that we're going to define on it? This is something that is objectively given in the sense it is determined by the data of the plot. So precisely the sigma algebra will be the one generated. So it's the constant sigma algebra that makes those functions U composition. Okay? Very sadly, this is a point that many professional decision theorists do not understand. It's very sad because this framework is necessary to be able to talk about information influence. Okay? Okay, so having said that, so the first, this point essentially to give an introduction to decision theory, there are many places to start, but possibly a good place is the Finetti's theorem that is a lot of that. It's a little covered, but it's the crowning glory of the Google days. And the Finetti's theorem is something that is based on following idea. So suppose that you have a decision maker that is able to rank these alternatives, so these functions with a position A by means of real value functions V. Okay? So the idea is that you associate F to a number which tells you how much F is worth. Okay? So Finetti asks the following question. What properties must we have for the decision maker to be considered a rational? Okay? And this is where we're going to be using that intuition of considering F as an asset that pays contingent on the realizations of the
quick question, but I guess we're going to answer to this. Well, the meaning of rationality that you have for
yes, will be. Okay. So, as I was saying, think of F as an asset. VF will be how much this asset is worth to you, which means that you will be willing to buy at any price less than your valuation, and you will be able to sell at any price higher than your evaluation. Now, envision a situation in which you can trade assets in this. So the idea, the criterion of rationality of Finetti is a decision maker is rational if he or she is in built. What does this mean? It means that there is no sequence of trades to the new decision maker that will guarantee you a strictly positive. Okay, if I am the decision maker, pretty much if I am rational, according to Finetti, you cannot explore it, you cannot objection. Okay? Okay, so if I give you a little bit of time, which I'm not going to give you, but most likely you come up with these three conditions that are necessary to be immune to arbitrage. These three conditions are that you should evaluate the constant functions that takes value 1, that if F dominates G pointwise, you should evaluate F more than G, and your evaluation function must be additive. The evaluation of F plus G must be the same. So just quickly, for instance, consider the first one. Suppose that I evaluate the constant function 1 more than 1. Okay, then evidently there is a price, let's say 1 plus epsilon, which is below my evaluation, and is above 1. And so if you offer to sell this thing to me at this price, I will be willing to buy it because it's below, the price is below my evaluation. Now, this is like a bond. Okay, so today I pay you 1 plus epsilon. This is like a bond. Tomorrow I own the bond because I bought it from you. States is realized you have to pay me the return of the bond, which is 1. So I gave you 1 plus epsilon, you give me 1, your profit is strictly possible. Okay, so this is, and the other ones are pretty much the same. So here, for instance, in 3, if the valuation of the sum is greater than the sum of the valuations, what you would do, you would you would buy from me F and G, then put them together in a portfolio, F plus G, and this gap between the two allows you to make a profit. Okay? Okay, so once you have made, as you can see, these very simple considerations, and as soon as you have come up with 3 observations here, these 3 properties that you must satisfy to be rational according to definity, it doesn't take that much to see that these 3 properties imply that V must be a linear function. And so once you have reached this conclusion, then by its representation theorem, along with the first 2 properties, normalizations of positivity, you conclude that V must take the form of an integral with respect to probability measure, and this is the expected utility. So in a way, this is where the expected utility criteria comes from. Notice that it doesn't come from considerations about uncertainty and probability. It comes from this idea of pressure. Okay. Questions about this? Okay, so I will talk about relations with other fields and applications later, but there is one that it's worth doing right away in the name of efficiency, and it is the following. So it's simply observation that you can rephrase this exact reasoning in a completely different way. So this setting is that of financial markets, where you now think of V of F as the pricing function. So the function that associates to F, it's price. Okay? So now, if you just, again, if I gave you at least a minute to think, but I will not, you realize essentially immediately that the same reasoning can be rephrased to say that if you are on financial markets and there are no frictions and there are no average opportunities, then the pricing function must be linear. Okay? So essentially, no average opportunities is the same as before. It's just that you transfer stuff across markets. No frictions means that you have to be free to transfer it anymore. Okay? In this form, this is known as the fundamental theorem of asset pricing.
So basically, it's kind of the other sense of the, if you have a kind of if and only if, you have like the statement, if there are no frictions and no arbitrage opportunities, then we get linear, positive, and normalized. Is again saying what we were seeing before, right?
Here the converse. Exactly. So the converse would be linear, then there are no frictions and no average opportunity. Yes, setting of markets, it is true. It is not, the converse is not automatically true in decision theory. The converse is true if you assume that these are the conditions and the pricing function is an ability. Okay. Okay? But you have to have at least a notion of equilibrium that is compatible with this idea. So just an observation about terminology. You know now that this function has this form in this setting, the measure that represents this function is called the arbitrage measure. Okay, so essentially, we have got to expected utility, and before that, essentially, there are some obvious questions that you can raise from this conclusion. What if there are friction? And if there are friction, you can ask what the form of the pricing function will look like. And if you find an answer, then you will go back to the decision theory. The decision theory has to set what is the equivalent of frictions. So for the moment, I leave them hanging, but we will be answering these questions a little bit as we go along. Okay, so we got to the Finetti's theorem, expected utility. It's a pretty glorious conclusion. So a necessary condition for somebody to be rational, at least in that sense, is that this decision maker would use an expected utility criteria. So evidently, this type of conclusion has sparked a number of works axiomatized the expected utility criteria to express these criteria in terms of restrictions on behavior. There are many axiomatic systems that have done that. The most famous Savage system, Bauman, Fishman, etc. One system that I will be using throughout is this one. That is typically referred to as the Bauman system, that is in reality due to Fishman. So as you can see, it's pretty transparent. So it says that here this sort of order symbol represents the preference of the decision maker, preference over G. So you see here you require that it's completed transitive. Here, this is the set of alternative. AC is the set of constants, constant functions. So regard directly the alternatives as functions, because this allows you to read transparently the axioms. So essentially, this is one of the key axioms that essentially says that if you add the constant, you will not reverse the preference. This is evidently necessary to obtain a real value function that sets the preference. Monotonicity is transparent. You think about because functions. It's a condition in the Finetti's theorem. This is just an assumption of non-triviality. One key assumption, this is why you find it here in yellow, is that if you have two functions, f and g, that you evaluate the same way, then you have to evaluate the mixing convex combination of the two as the other. Okay, so keep this one in mind. Essentially, if there is something that you should really keep in mind, it's A2 and A6 for the moment. A6, because this will be an object of reflections as we go on. Okay, so this is the Finetti glorious conclusion. This is the axiomatization. Nevertheless, there has always been a mistrust in expected. Why? Because this function does something that at least decision theorists refer to as the complete reduction of uncertainty risk. What do they mean by this? So normally in decision theory, you designate as risk those situations where you can assign probabilities to all relevant events, as opposed to uncertainty where you cannot use. Okay? So in general, if you casual observation, think of climate change, think of foundations of quantum mechanics, think of stock markets, think of universe. The idea is that in most situations, interesting one is not able to assign probabilities to. And this is essentially the source of the mistrust toward expected. You could push this a little bit further and realize that there are things that should not exist if you were always able to do this. Notably, this would be why. It should be very familiar with it. It should be doing robust optimization if you then reduce your uncertainty. Okay, so these ideas essentially started to take clear shape mostly in the 60s and in the 70s. On one hand, with Ellsberg experiments, I don't know if you know them, 20 celebrated, I'm not going to go to them, but and another stream was the development of portfolio theory. And so these ideas, this issue about uncertainty versus risk, led to a modification of the axiom. Notably, the first modifications consisted in changing the sixth one. In which way? One modification is the following, where you see you, given the same condition, you replace difference right with the weak preference. So this means that essentially you're going to be having a weak preference for mix. Okay? Or if you think that think of two functions. Okay? When you mix two functions, unless these two functions display example of variation, or one is constant, meaning they go to school to meet, or one is constant, and when you mix, you reduce the variability associated with those functions. And so this is why this idea expresses an aversion of variability. You prefer less variability to more variability. Or equivalently, in finance, this represents the value of energy. So when you replace the sixth axiom with an axiom of this form, you get what's called the Maxmin expected utility function, that is a function of this form. So here you have a set of probabilities rather than one probability that you expect to be. So for each probability in the set, you calculate the expectation of the function, and then you take the lowest expectation. Okay, which in this way you express a sort of a cautious attitude that is the reflection of your aversion to variability. Okay. Another modification is the following. This here essentially you keep part of the original sixth axiom of expected utility, but you make a weaker demand in the sense that you require that the axiom be valid only for functions that are commutative. Commutative functions are precisely the ones that go to it, that mathematically have the same level of variation. So this expresses what? This expresses that you're not going to reduce the variability if you make something that display exactly pointwise the same variability. And so once you replace the expected axiom with this axiom, you obtain this representation where the difference is with respect to the expected utility is substantial despite the graphic similarity, because here the nu is not a probability measure, but it is a capacity. So this means what? A capacity is a set function that is not necessarily added. The probability of a disjoint union, probability of A union B when the joint is the sum. This is not necessarily true if the object is a capacity. And consequently, the integral that you find here is not the Lebesgue integral, but it's something that is called the Choquet integral, and in particular, it's not. So the theory that emerges for there's two theories that emerge for this modification end up being substantially different from expected utility. Okay, questions?
So again, in the one before, we have basically the expected utility was the minimum over all the possible probability. Well,
the evaluation was the minimum expected utility over those.
But it was still a Lebesgue integral. In this case, we get
the integral is a Lebesgue integral here because you take it with respect to the probability.
Right.
And then you take the minimum family of Lebesgue.
And how do you choose the set of probabilities in the other one?
So these ones are they come from the axiom. Okay.
Yes.
And so once you satisfy the axiom, I will get to this, but essentially you first show that the first 5 axioms imply the existence of this set.
Right.
Okay. This set of probabilities. And then the 6th axiom pins down properties of this function. In particular, if you use the 6th axiom of expected utility, it's linearity. We will talk a lot about this, but formally expected utility is something that goes through set C. And that expresses, if you think of one time, this is the way they used to teach Bayesian statistics. They will tell you that Bayesian statistics is not The real paradigm is that you're uncertain about the probabilistic description of it. And so you have a statistical model that is made of a set of things. You're Bayesian, and therefore you have applied over this probabilistic description of the words, and with this plan you take an average. Okay, and this is the predictive in Bayesian statistics. So essentially, this is what happened from the 5 axioms to the 6th for expected utility. The whole thing, you take an average since you summarize this family of things by one probability, the whole thing becomes in. Here, essentially, one concept that we'll be pushing, clarifying momentarily, is that all these models are really averages over a set C. The only thing that averages are not taken in a linear sense, as we used to, but this is a type of average. I mean, minimum is a type of minimum of this sort is a type of average. The idea of Choquet integral is another type of average, but these averages do not be. Okay, so essentially, one should be taking first 5 axioms set C, 6th axioms type of average. Okay, so maybe I should postpone the answer. Yeah, let me say that just to give a little bit more of a feeling for this thing. The structure of this proof is actually very simple. If you go back to the, I'll take the axioms back in a moment, but it's pretty evident that the first 5 axioms imply these trigonometries. This comes essentially from, they do it all together, but the key axiom for this is axiom 2. Imagine take a constant h that is equal to 0. So let me go back to the axioms. In this one, we got them as functions. Okay? Suppose that this is the function 0. The axiom must hold. Okay? Alpha, these are convex combinations, implies a sort of positive homogeneity. Technically, you will extend just on 0, 1. You will extend, so F referred to G implies alpha F refers to alpha G. You will extend with the technicality as complete positive homogeneity, but you can read it automatically here. Positivity is automatic. If this is a function, these are it's pointwise dominance. Okay? You have to respect pointwise dominance. Do you understand what I'm saying? You remember when, so this is in the end a set of axioms as to end up with the function, like the green definition. Something that assigns numbers to functions. Functions are the object of choice. So once at the beginning we had identified alternatives to functions, a preference becomes what? The preference becomes an ordering to establish among a set of functions. Okay, so now the issue that we ask here, if you respect, if your order displays this value, these preferences, okay, can it be represented by means of a real valued function, which means F referred to G if and only if B of F greater than B of G, and what this B would look like. Okay? Okay, so now, if you look at it, first of all, essentially this axiom, you need the combination of the other one, but mostly this axiom does the job, along with A1, guarantees you that this functional exists, that this functional that associates functions to numbers. Second, now this functional has to describe this order. So now this part tells you that if you evaluate F more than G, you should evaluate this more than this for any alpha. Okay, so now one thing, suppose that H is the constant function equal to 0. Okay, so this axiom tells you if you prefer F to G, B of F must be greater than B of G. And this one tells you that B of alpha F must be greater than B of alpha G. Doesn't take that much to see that if alpha is positive, this is positive homogeneity. So it has to be with the load cancellation. And essentially, this delivers immediately this positive homogeneity restricted to a coefficient that is in 0, 1, once there is a small technical step to show that this implies positive homogeneity. Now, monotonicity is what? If you write them as function, it says if f is greater than g pointwise, you should evaluate f more than g. Okay? This is referred to as the monotonicity of the function of the positivity. Okay, so the point here was that these axioms pretty much imply rapidly that the functional exists, is positively homogeneous, monotone, and there's another property. We'll return to this one. So now, V of f greater than V of g must be equivalent to V of this greater than V of this. Regard it again as an algebraic law of cancellation. So now this must be what? It must be that V of alpha f, V of this must be equal to V of alpha f plus 1 minus alpha plus B of 1 minus alpha h. So this part, the constant can be taken outside. Okay?
Because B is linear, right?
No, this is constant. This has to be constant. So if you don't require that h is constant, in fact, you could merge these two and it would become linear. Here you require just that it will be additive over constant. Okay? And this is the same thing, at least think of it. In RM, you have the constant vector, web vectors. What do you do? Translations of the vector. And so this is transparently referred to as translation invariance. So the function doesn't change anything if you translate everything. Okay? And so maybe, clearly one should give you a little bit of time to go through this, but point is that this is not that it's pretty transparent. Contrary to what other people might tell you, but it's transparent. It takes 5 minutes. I didn't give them to you, granted, but once you observe this is why I'm saying this, because it's the structure is, in a sense, up to a certain point, pretty easy. Problems appear later, but there is no reason to make such a big deal about this stuff. Once you have these 3 properties, there is another very simple argument, probably not visible immediately, but that these 3 properties together imply the sublime continuity of this function. And as I said, at this point, you can show, not going to show, that all these functions are associated to a set of functions, all functions, along with the normalization. So B of 1 is equal to 1. All these functions that have these 3 properties on pretty much on any Banach space are associated. Okay, so not on any Banach space, but probabilities are an elements of duals. So if you regard them like that, the statement is the same for any Banach spaces. Otherwise, any time that you can identify the dual to a space of probabilities. So this is the first 5. Once you add the 6th, then the one unexpected utility forces the linearity, and we have its representation here, and you have the Lebesgue unexpected. This one, remember that you have positive homogeneity. Now you can regard the 6th axiom as a requirement of concavity. Okay, you prefer the average over, remember that f is equivalent to g. Okay, so that would be you prefer the mixing over half B of f plus half B of g, that is B of f. Okay, so now positive homogeneity can concavity is superlinearity. Instead of using a theorem of representation for linear functions, you have to use one for superlinear functions. This is sort of a bit of a folk theorem, but as far as I know, the first proof was given by Ormander, and that gives you the form Maxmin expected utility. This one, evidently, what can it give you? It can give you linearity restricted to a monotonic function, because essentially this is where the requirement that you have made, and there is a paper by Schneider in '86 that gives a representation for functional set of these three properties plus monotonic additivity and shows you that they have to take the form of Choquet. Okay, and so this is how this essentially the mechanical this thing works. Okay. Okay, so having done this, I had mentioned that everyone, then I would go back to that issue, that parallel between asset pricing and rationality. Evidently, once this model had been obtained, there was this idea of saying, okay, so we know that the net incorporation in terms of the equilibrium of the financial market, if there are frictions, the pricing function cannot be linear. Now, these are functions that are non-linear. What kind of frictions are associated with these functions? So there is a literature that actually is ongoing that has identified for various functional forms the frictions that produce the functional as an equilibrium pricing function. I've shown that some types of incompleteness in the markets, restricted participation, generate pricing functions that are Choquet integrals that are of the form Maxmin, etc. You could go back now to decision theory and ask, okay, but then what does it really mean to be rational? What are the equivalent frictions, etc. I would like to do that, but if I start doing this, that would be a little more. So we move on rapidly. Okay, so further developments, these ones essentially, I'm going to mention them only because you will see popping them up as examples in the second part. I won't go to the details, but one paper that in my opinion is very important in decision theory is paper by Invariant, where they focus on the first five axioms and show that the first five axioms imply that the representation of the function is always small. So it will always be a convex combination of Maxmin and Max with variable coefficients. So the coefficient varies with the function to be evaluated. This is, as I say, in my opinion, an important paper, which in particular, because it has brought in both new ideas and new methods. One thing that turns out to be very important, both conceptually and technically, is that they identify how you determine a set of problems, set of possibilities. And so they showed that essentially think of somebody that maybe you or Maxmin expected. Okay, and what I can observe in principle your preference, you choosing between F and G, G and H, etc. And I can in principle write down your function. In terms of numbers. So what is your set of primes? They showed that this set of primes is the Clark differential of the function P at Z. And I leave it at that, but
the alpha is a function, so basically we can represent it through F, so we can compute it.
Actually, you really have to, it's very difficult to compute the alpha. It's easy to compute the alpha. Okay. And then you derive, of course, once the B, sorry. Once you have the B, evidently there is an obvious equation. Okay. That gives you the solution in terms of alpha.
So, okay.
If you're concerned about something that is totally legitimate, which is deriving these functions from data.
Yeah.
That's what we're to do. Your setup is B.
Okay.
Just, I suspect that the representation theorem says that there exists some alpha that will make it satisfy this formula. But what is the restriction on alpha? Can it be any function of it? Or?
No, actually, it cannot be any function of f. Okay, to begin with, this is between text value 0 and 1. Then it has some form of so the alpha, if you given value text f, values that it takes on f plus a constant function is the same. And there are a certain, you can see all the restrictions that are on this alpha, just suppose that the minimum and the maximum are not at a certain f are not the same. Solve for alpha f. Okay? Then you see that any property of V that you impose, positive homogeneity, translation, etc., implies property of alpha. Another development of this model, okay, why this model is important? Because as I said, this is the class where we have already placed expected utility, Maxmin expected utility, Choquet expected utility. So in a way, this is the reference class. There is also another class which we'll talk about in a second. I worked on this same model, and I provided an alternative representation for the P like this. So here this is the collection of expected utility before, but here you see that you have a double integral. The outside integral is taken on space of probabilities, and this is not a probability, it's a capacity. So essentially, the content of this representation is twofold. One, that this reference class, 1A5, essentially this representation shows that the idea of Choquet integral is a unified idea. And second, it gives meaning to something that we have been saying for years, that this was a neo-Bayesian approach. Now, this shows why this is a neo-Bayesian approach. Why? As I said, if this is a probability, this is the double integral of Bayesian statistics. Okay, you take an average over the probabilities. So this shows that essentially all these theories that come from this framework of a 1A5 are theories that have this form. You have a statistical model, so you're set about a set of probabilistic description of the world, and you take averages of this statistical model. The difference across these ideas is in the idea of average. Linear average expected utility, no linear averages of these theories. And for us, essentially, this was important, and in particular for me, about what I'll be talking later, because the application that I've always been most concerned with is to the foundations of statistics. So to create this bridge was something that was important. Another development, recent development, also the reason why I'm mentioning this is that there is a possibility that this is something that you might have encountered or you might encounter. This one, for instance, this is another modification of the axioms where you use the Maxmin axiom as a sixth axiom, but you change axiom 2. Essentially, what you kill here is positive homogeneity of the function by this change that you make. And by eliminating positive homogeneity, so here you retain concavity, but you kill positive homogeneity, so the functions are no longer. Okay? The representation takes the form. You see, it's a little bit like Maxmin, but the difference is this additional term that is to be interpreted as some sort of a penalty function. So this is the cost of evaluating f by q. Why am I mentioning this? Because these models are very common in robust statistics, and most of that literature, for example, in regression analysis that uses penalty functions, not often is founded in this work, but it should, because this is where things start making sense. If you look at this work in robust statistics that started in the 80s and is still ongoing, this work makes this pretty clear. In the popular model, what you typically find is that this function is typically expressed as the cost of departing from a reference probability. For instance, you might have encountered models like epsilon contamination. There is a reference probability, but then you want to robustify by considering probabilities that are a little bit distortion of the given probability. And so the idea is that if you use them to evaluate, you pay some sort of cost. The most popular model is the model where this function, expressed as a penalty from a reference probability, is the relative. Another model that is not a problem, one this is something that you might have encountered. It's very common in statistics. So this is a probability. So if you eliminate the phi, this is double integral, this becomes expected utility. So essentially nothing happens. Nothing interesting happens in statistics. One thing that is done for many decades is just to put a nonlinear function in between. And so essentially this model just follows axiomatically this procedure. The axiomatic here is a little bit more important, but this is the purpose of this model. There is an equivalent representation that I prefer to this one, which is this. So where you see you have here the phi is strictly increasing, so it has an inverse. You can write the model in this way. And strictly increasing doesn't change the order of things. But I prefer this because it makes it clear that this is an axiomatization of a well-known ways of taking means, that is the quasi-arithmetic means. This is an important thing, axiomatized by Kolmogorov. We know lots about quasi-arithmetic means from statistics, from Margaret Woodbury. So this is another model that has. Okay, so pretty much, for as far as I'm concerned, for the second part, this is the stuff that I wanted to cover. So now let me share a little bit more time, but essentially I want to give you an idea in terms of applications of fields where these ideas are immediately can be spent immediately. So I said, we have already seen that there are two parallel theories, decision-making and equilibrium asset pricing. A third parallel theory is the one of risk measures. This is a central field in mathematical finance. You also find it a lot in insurance for premium calculations of value, etc. It's also used a lot and increasingly in engineering, both for similar purposes and in risk management, but also, and I'll make another example momentarily, for the evaluation of complex systems. So here, modulo technicalities on the domains, it's the same thing. So this is a decision theoretic function, you change signs, you get the risk measure, and vice versa. Why? Because here you measure risk, and in the other one you measure utility, because the theory is exactly the same. Something that incidentally lends itself to basic games, both of decision theories and finance people, to write what people want to, but they write it to the other field. And that includes myself. So it's, but this is to tell you how exactly the same these two theories. In finance, these are interpreted as indicators of the riskiness of a portfolio, line of business, company financial position, etc. They're practically very important. Why? Because there are these things called Basel accords that are accords that are made roughly every 5 years, which determine the risk capital market operation that can be undertaken by financial institutions. So effectively what happens your bank, you want to make an investment, these accords stipulate that you have to use a certain risk measure, put in the data that are produced in a certain way, and in this way determine the collateral, for instance, that the bank has to put in order to undertake this investment. And so the idea is that in this way we have the crisis. The accords specify exactly what risk measure we have to use. This used to be a risk measure called the variant risk that was introduced by JP Morgan in the early 90s. Now it's been replaced by another measure that is called the expected shortfall.
And these accords, they're among banks or?
Yes, so there are worldwide guidelines for financial institutions. I don't know if you know, but this is an extremely sensitive subject. There is this guy, I'm not sure whether you heard of him, is popular literature. It's famous for a book called Black Swans. And this guy is a former financial consultant, testified before the US Congress asking that they would ban the variant risk, which according to him was the cause of the crisis of 2008. So you can imagine that it gets extremely heated in these things. This one is something that is again very closely. I don't know if you've ever heard of it, but actually in computer science it's pretty popular. They're called ordered weighted averaging operators. They have been introduced in 1988 by Jaeger, and they're widely used in soft computing and also in evaluation of complex systems. A trend of the moment is their applications in cybersecurity. This is a huge field, and to give you an idea how people do these days, rather than say substantial things, they do numbers about citations. This guy has 90,000 citations only in this. So you can imagine that it's a pretty big field. So technically, these are the same as decision theory functions and risk measures. In fact, a special case, since here everything is done in finite dimensions, unlike decision theory and risk measures, where typically things are in infinite dimensions. In fact, the original law are Choquet integrals with respect to a special type of capacity. Permutation invariant capacities are the equivalent of uniform measure, but there are lots of permutation capacities and non-uniform measure. So for soft computing, you would have to, if you don't know, you would have to look at it, but it's too long. But for this is very simple to tell you how this is used for the second bullet. In the second part, one thing is that the states in decision theory correspond to different dimensions along which a system has to be evaluated. And so the idea is that you want to aggregate these dimensions to get a summary indicator that will allow you to choose among different systems. Another usage that has been done on this, instead of having different dimensions, you have a single dimension, but you have different groups of stakeholders that evaluate this thing in different ways. Of course, you can manage the two. And technically, what you get is again something of the form that you have seen before, and essentially we can interpret anything that you've said before in this set. Okay. So what else? Okay. One thing that I want to take two things. One is this is the most common application that essentially is giving a lot of relevance to decision theorists and whoever does these things these days. It's this model uncertainty that becomes some sort of a scientific paradigm. So the idea is in whatever field you are, you use models, but you are unable to say how accurate your models are. You cannot pinpoint boundary conditions, etc. And consequently, you cannot accurately predict phenomena, evolution, system responses, etc. So just think, for instance, one thing that today is very popular is the use of these ideas in climate change, but this type of observation is dominant. So this problem about uncertainty about the model that describes the phenomenon. But take, for instance, how fundamental this issue is for the very idea of a machine learning. And so because of that, these have become typical applications of the ideas that I have illustrated. Okay? 1 minute, okay, 1 minute is perfect. Because, so, I have not spoken about the foundations of statistics because this will be the subject of the second part of the talk. One observation that I can make in this minute is the following. There is an evident link, probably not telling it to many decision theorists, but I'm sure it will be evident to you, that between this problem and the problems of dynamic extensions. Why? Because if you have to do dynamics makes sense when you, as you go along, you get new information, you have to change your mind on the basis of new information, etc. So the issue is that if you don't know how to process information, if you're not making inference, this is, I like putting this quote, because you know, I like these two people a lot. These are Schmander, we have already encountered. This is the guy that invented Choquet expected utility. The two together, they invented Maxmin expected utility. And this is what they say, about models that cannot not have a dynamic extension. So again, we're wasting time. I believe that the reason why this model has not been successfully extended is because we have been lacking theories of how to process information in a context that is not based. Evidently, maybe I should have changed this order, but if you do not know how to process information, you cannot do an inference, therefore you will not do mathematics. And so this again leads us to as a special motivation for the second part that is would be about building statistics on a low Bayesian. Okay, well, that's